This is lesson 2 of the GCSE motion topic entitled Distance Time Graphs. By the end of the lesson you should be able to recall that a journey can be described by a distance time graph, be able to interpret a distance time graph, and be able to perform calculations using data from a distance time graph. Before we get going with today's lesson, just a quick recap of what we did last lesson. We're looking at how to calculate speed and velocity. Speed is the distance divided by the time taken, whereas velocity is the displacement divided by the time taken. Displacement being a distance travelled in a straight line in a given direction. Okay, so just to give you some further practice at those then, what I'd like you to do again is using in your exercise books, there's no need to write out the questions here. What I'd like you to do is to answer those questions, and we'll go through those in a moment. So if you can pause the video, have a go at those, and we'll go through the solutions in a moment. Okay, so given your practice on Isaac Physics, you should be well versed with these, so I'm just going to give you the solutions here. So the first one should give me an answer of 10.4 meters per second to 3 significant figures. Question 2, 24 centimeters. Question 3, 4.4 seconds. Question 3, part 2 as it were. A, the speed is 24 miles per hour and the car's velocity is 20 miles per hour due west. Notice we've given a direction here because it is a velocity. It needs a magnitude and a direction. On to today's topic then, distance time graphs. It might come as no surprise that a distance time graph has on the y-axis distance, in this case in measured meters, but it could be kilometers, it could be miles, and we've got time on the x-axis, and again this is in seconds, but it could be in hours, it could be in minutes. It's dependent on what you want to put on there, what's appropriate for the actual journey here. Okay, this is a little animation. It's going to run through the journey of a car, and I'm going to pause it and explain the features of the graph as it runs by. Okay, so let's get the animation going. And the first thing to realize is that the car is traveling at a nice steady, constant, or sometimes referred to as a uniform speed. Okay, so when it's traveling at a constant or uniform speed, a distance time graph looks like this. You've got this nice, straight, diagonal line. Okay, so something traveling at a constant speed will give you a nice, diagonal, straight line. Okay, I should point out that the distance here is the distance measured from the starting point of our journey. Okay, so currently he's about 20 meters away from home. Let's start the video. Now when the car is stationary, time is still going, the stop clock's still going if you like, but his distance away from the starting point has not changed. So a horizontal line on a distance time graph means that the car is stationary, standing still. Now over this portion of the journey, the car starts to move off again, and you can see this time that the slope is steeper, and the slope is steeper because the car is moving faster. And then the car remains stationary again for the remainder of the journey. Okay, so that's our little story of our journey. So you could be asked at GCSE to interpret what's going on here. So we've got a nice constant uniform speed here, then stops for 10 seconds, and then sets off again but at a slightly faster speed, and you can tell this because the slope is steeper, or the gradient is steeper, and then is stationary for the remaining 10 seconds of the journey. Now, in addition to describing the graph, you could be asked to perform some calculations. For example, you might be asked to calculate the speed over the first 20 seconds. So how would we do that? Well, first of all, we'd turn it into a kind of triangle again. So if you want to work out speed, it's distance divided by time. The distance travelled in the 20 seconds is 20 meters, starts at 0, finishes up at 20. So 20 meters travelled in 20 seconds. Pop that into our formula. 20 divided by 20 gives us 1 meter per second. Again, the unit is meters per second because we measure distance in meters and time in seconds. Okay, we know over this period is stationary, so the speed would be 0 meters per second. What about this section here? Okay, well this time we'd adopt the same approach. We'd turn this into a little triangle and we'd use the same equation, speed equals distance divided by time. So let's have a look what that looks like. Now, there is something which people often trip up on here. They think, oh, the distance travelled is 60 meters, but remember he's already started. The point at which he started the journey is already 20 meters away from home. So over this 10 seconds here, he travels 60 minus 20, which of course is 40 meters, and they've done it in 10 seconds. So do watch out where you're starting from on a journey. Okay, so let's continue with that then. So put our numbers in and we end up with 4 meters per second. Remember I said that when a car is traveling, an object is traveling faster, the slope of the graph is steeper, the gradient is steeper. Okay, and there we have the complete picture. Okay, so we need to get something into our notes for that. So could you put the title distance time graph, and can you make a copy of this please and insert coloured clouds into grey clouds. So if you'd like to pause the video, then I'll go through the solutions with you. Okay, so it is a distance time graph, can be used to see when an object is stationary or travelling at a constant speed. The steeper the slope, the faster the speed, and it's the gradient of a distance time graph that shows the speed. Okay, let's move on. And again, I'm afraid this is for your notes. You'll have to make a little sketch of the graph that we got there. It needs to be no more than a sketch. And then what I'd like you to do is to have a go at those 4 hopefully straightforward questions. So again, can you pause the video and can you work through those questions please? Okay, solutions then. What is the speed during the first 20 seconds? Well, speed v equals distance divided by time. So after 20 seconds he's travelled 10 meters, so it's 10 divided by 20, which gives you 0.5 seconds. Question 2, how far is the object from the start after 60 seconds? This often fools people because all you have to do is read from the graph here. So 60 seconds up, they've travelled 40 meters. What is the speed during the last 40 seconds? This is trickier, and I should point out here that when you get a line going this way, so far we've only talked about positive lines here, lines with positive gradients, then it means it's simply returning back to where they started from. Okay, so we're just going back on themselves. So the speed during the last 40 seconds, speed equals distance divided by time. The distance travelled will have travelled 40 meters, 40 minus 0, but the time taken is not 100 seconds, it's 100 minus 60, because it was already 60 seconds of the journey had already gone by the time it got to 40, so it's that time there, which is 40 seconds. 40 divided by 40 is 1. And then question 4, when was the object travelling fastest? So you're looking for the steepest slope here, and hopefully you can see that that's between 40 and 60 seconds. I've set you some more Isaac Physics exercises for you to have a go at that. There aren't as many as there were on the previous exercise, so good luck with those. You should now be able to recall that a journey can be described using a distance time graph. Recall that on a distance time graph, the steeper the slope, the faster the speed, and that a horizontal line means that an object is stationary. You should be able to calculate the speed of an object by calculating the gradient of the slope.